Alright, so hi everyone. In this video I'm going to explain few topics of elementary number theory. So I will try my best to cover as much as topics as I can. So a little bit introduction of topics that I'm going to cover or teach. That is fundamental theorem of arithmetics, introduction to divisibility and greatest common divisor, prime numbers, the fundamental theorem of arithmetic, that's what I already said, sorry, the series of reciprocals of primes, the Euclidean algorithm, the greatest common divisors of more than two numbers, the arithmetic functions and internet multiplication, the introduction of Mobius function, Euler function, relation between these two, and the product formula, and then we have Dirichlet product, inverse, Mobius inversion formula, and also the Mangold function, multiplication function, completely multiplicative functions. And yeah, this is pretty much I'm going to cover, and I will also try to cover the related theorems as well. So first topic that I'm going to give you, the first before starting any topic, I want to highlight some of the basic concepts that will be useful for you throughout this content. Alright, so we have divisibility rules. Alright, divisibility rules. These are pretty much easy. We already know this from our preschool. Alright, so just giving you some example. There is one of the divisible that we call that n divides n. We call this as reflexive. Alright, reflexive property. This sign denotes right over here divides. Alright, yeah, we can write it as n divides n, or you can say if you put some number instead of n, that is you can write 2 divides 2. Alright, because we know that 2 is dividing this 2. Alright, this denominator 2 we are writing over here, and the numerator 2 is writing over here. This thing is dividing this. Alright, this is the simplest way to say that n divides n. One more thing, let me adjust the focus. Okay, I don't know why this video looks flash out, but sorry for that. I'm using webcam right now. Okay, this is one of the property, and this is another property that is we have to consider knowing. If for example d divides n and n divides m, we can say that this d divides m. Alright, you can put some numbers and try to do yourself. Take some numbers which can divide this. Take d number that can divide this n number. Take your own numbers, and you can see that this d basically divides this m. So this is pretty much easy. You can also prove this. That is, let's for example, we are saying that d divides n, so there must be some integer, right? For example, d into some k equal to n. We are getting this n, so we can say that this d is dividing this n by some number. This k belongs to integers. Alright, and throughout this number theory problems or the content, we are going to use mostly we are going to deal with mostly positive integers. Alright, so we have this d divides, and also this n divides m, right? From here n divides m, so we can write m equal to some k dash n. This is different integer, this belongs to different integer, and from this we can write m equal to k dash kd. Alright, substituting the value of n, you will get m into taking out the d and making this 2k's common. As these 2k's belong to integer, we get some d into some k double dash, for example, instead of this 2 case I have written it. So from this we can say that d multiplying by some integer, you're getting m, so that implies d divides m. So we got this one. Alright, this is pretty much easy. And one more thing that I want to add here is another property which is easy and used many times, that is d divides n and n divides m. That implies d divides an plus bm. We call this property linearity. Alright, so we can prove this also. Alright, take the value of this. You can just replace this as I have earlier did with the d divides n, and take some value for n divides m. Then that implies that whenever we use this, whenever we add the values, you're gonna eventually get the this form that is d divides both a and n bm. Alright, this a and b are the linears. Alright, so these are the variables that could be different in this case. And right, this is pretty much that we usually use in here. And moving on to start some of the theorems related to. Alright, right, now first theorem that I'm going to consider is common divisor, that is GCD. And in that GCD I'm going to use this linearity, alright, linearity property. Okay, the theorem says that theorem, alright, given any two integers a and b not equal to 0, there is a common divisor d of a and b of the form d equal to ax plus by, where x and y are integers. Moreover, every common divisor of a and b divides this d. So that implies we can say that d is GCD of these two integers a and b. And yeah, that's what we have seen, that this is a linearity form for a and b. Alright, now we can prove this. It's pretty much easy. Alright, so what you have to consider while proving this is that there is a well-known principle, that is we call it as well-ordering principle. Alright, well-ordering principle, it says that every non-negative integer has the least number. Hence, we can conclude from this that the set is not empty. I don't know whether this is visible clearly or not, but this is what right now I have the chance or option to use, but soon I will try to upgrade and use some different camera or something, but for now I have this only. Alright, now so we are proving this theorem. To be honest, I'm not going to give you clear steps. I'm just giving you the analogy behind the theorems. So first, what you have to do, that the set that you're considering, this set, the set that you're considering, because you want to prove this, right? Ax plus by, you want to prove this. Alright, so you're saying that this set that you're considering as is non-empty. Just by proving that this is non-empty, that is, there is a minimum number exists in that set, that we claim that this number would be the number we consider as remainder. Alright, so we are seeing that here in this set there is a non-empty, this is the non-empty set, and this set has a least number. Alright, and we call that number as R, will be lesser than D, and R will be greater than or equal to 0. Alright, now to prove that D divides A and D divides B, because this is a common divisor of these two values, so we have to consider Euclid algorithm that we have learned in previous classes, that is A equal to BQ plus R. Alright, where 0 is less than or equal to R is less than D, and we have Q belongs to Z. Alright, this Q, this is a quotient. Now we know that R should be 0, or if R is not equal to 0, then we can get R equal to, from here, A minus BQ. Right, that implies R equal to A minus AX plus BY into Q. From this implies we get A into 1 minus XQ plus B into minus YQ. We get R equal to A into 1 minus XQ B minus YZ belongs to S. Here we have to know that we know that R is greater than 0, R is less than D, R belongs to S. We know that, that's what we have considered, right? R is not equal to 0, so we know that R is greater than 0, R is less than D, but it is less than D, and this R belongs to S, so that means R should be less or the smallest of all, right? Well, for that we have to add something up. Wait a minute. Alright, so R should be less, right? From this we can say that since this R equal to A minus BQ is given, so basically this, instead of this A minus BQ should belong to set S, and we know that A minus BQ, 1 minute. Alright, sorry for that. I got a bit confused between two theorems, to be honest, and we have to end this up right over here, because this R that we got from multiplying this A with some integer and B with some integer. Alright, this entire R belongs to S, so R is getting completely divided by this. So if what we have assumed that r is greater than 0 and r is less than d and r belongs to S. So that implies that is actually meaningless, to be honest, and from that we can conclude that r should be equal to 0, right? A equal to dq, that implies d divides a, and similarly we can write for b, that is d divides b. Alright, so this is pretty much about one of the theorem that is related to divisors, and next theorem that we have here is theorem that proves that GCD has the following. We are proving the properties of GCD basically. Alright, so where we have to prove that GCD properties, one of the property is that a comma b equal to b comma c, that is b comma a, the GCD of a comma b equal to b comma a. Whenever I write like this, that represent the GCD, for example d equal to a comma b. So what I'm trying to say is that d divides a and d divides b, and d divides there is another number that divide this a and b, so that number also divide d. So at the time I am considering this d a as a GCD of two numbers. Alright, now for this we have to prove for example the GCD of, we are assuming that the GCD is different, so the GCD of a comma b will be equal to d I'm considering, and the GCD of this okay, let's take this one and try to represent. So we know that whenever we can use GCD, we can represent these numbers as a linear form. So we can represent it as ax plus by, where x and y are belongs to integer, x and y belongs to integers. And now x and y belongs to integer. Alright, x and y belongs to integers, so from this we can write d equal to by plus ax. Since addition is commutative, we can write from here, this is the linear combination of the GCD of b and a, that is equal to d. So from here we can write b and a. So we have use this and prove this. Alright, one more property that I want to include over here is that a comma b comma c, the GCD of a comma b comma c will be equal to the GCD of a comma b and c. Alright, so here we are assuming the GCD of this, that is equal to d1, for example, that is GCD of this entire equation equal to this. Now we can have the linearity for this, that implies that is equal to ax plus b comma c y, and I am assuming the GCD of b comma c equal to some d1. Alright, d1 I have already used, d2, so the GCD of b comma c I am replacing with d2. Alright, so d2 equal to bx1 and cy1, because we have already used x and y, so I'm using x1 and y1. So substituting the values in here in the linear form, that is we get d1 equal to ax plus bx1 plus cy1 into y. From this we get ax plus bx1 y plus cy1 y. Now I am just changing the parentheses. I get ax plus bx1 y plus cy1 y. From this I get the GCD of a comma b. Alright, I'm using these integers x and x1y, x1y, this is x1y as x dash, some integer, and y1 and y as some integer, some another integer that is I'm considering as y dash. That implies we get this this form. So that implies as we got this, that implies d1 is a d1 is that the one that is dividing this, so we get this d1 from here. Alright, so we are saying that, we are concluding that the GCD of this, that is equal to d1, that is what we have assumed, and we got this, and the GCD of these two are same, that is d1. Alright, one more property that I want to include is here is that a comma c and bc should be equal to mod of c a comma b. Alright, now the c is there. First we assume that d equal to a comma b, the GCD of a comma b equal to d, and the GCD of this entire is equal to a e. Alright, from here I get the linear combination that is equal to d into ax plus by. Alright, and I can multiply this with c on either side. I get cd is equal to c into ax plus by. Right, from this that implies that CD is a common divisor of one more thing that I want to do is that CAX CBY. So it's like the GCD, CD will become the GCD for CA and CB. So I can write it as that implies that CD equal to CA comma CB. So since it can be represented using the linearity form, so we got that CD is a GCD of CA and CB, and from here we know that CA and CB and BC have the GCD that is E. So that implies E divides AC, E divides BC. Alright, E divide AC, E divide BC. That implies E divide the linear combination of these two, right? ACX plus BCY. The same thing that we got from here. From this, that implies that the GCD of this is equal to CD. From this we got E divide CD, and from here we can write also that CD divides E, because I have used this and got this. I could also use this and got this, so there could be two chances for that. So from this we can write E equal to CD. Alright, these are two equal, I believe. From this we get equal to C into D. We got this one, right? Mod of C and the GCD of A comma B is a D. That's it. One more thing that is I want to add here is this: A divides BC if and only if A comma B equal to 1. Means we can represent this as a linear combination of two numbers, that is AX plus BY. These two numbers are X and Y, and we consider this lemma, Bizot's lemma, and I can prove this also. But for this, you just have to keep that in mind that A divides BC, that implies A comma B equal to 1. So that implies that A divides C. From this, if the GCD of B and A is 1, so that means that these are two co-prime numbers, and obviously this A cannot divide this B. But when we are using this C, that implies that A divides BC, so that means A is dividing C. So you can have some numbers and use a concept over here. You can get that A divides C, or else you won't get it. The condition should be A comma B equal to 1. Then only we can go, get this. I can prove this also. That is, I'm using this, so I'm multiplying this with Cax plus Cby, alright, or Bcby, whatever you want, and from this I can take out since we have A divides BC, we can write AK and BC. Alright, from this I can write, instead of this BC, I can write Cax plus, instead of BC I am taking this AK into Y, taking out A common, I get A Cx plus Ky. That implies A divides C. Alright, A is dividing this C. That is pretty much easy. One material that I want to include here is that it says that every natural, every integer n greater than can be is either prime or product of prime. Alright, so this is pretty much easy. Now we can say that, I'm just giving the analogy behind it. If n is prime, there is nothing to prove, right? There is nothing to prove, because this is what we got, right? N is either prime or n is product of prime. So now taking, if let n equal to 2 and 3, in this case the theorem is true, or we can say it's trivial case. So we are assuming that numbers from 4 to n numbers, alright, n numbers. Now we are proving for n, that is some number, that is random number that we am selecting, that which is greater than 1, basically greater than 2 and 3. So basically this n could be represented in the form of n equal to CD. Alright, so because we know that it is not prime, because for the condition for prime it is trivial, so we are considering that this number is not prime and this is composite number, so we can represent this number n in the form of C and D. Now by induction assumption, what we can do here is that we can write this C and D separately. C is less than n and D is also less than n. From here we can write C and D, both C and D can be written as product of primes, or else if not actually this C and D might prime. C or D belongs to prime numbers. Alright, if not, this C and D can be written as primes. If not, you can continue this process till you get the numbers or the integers belongs to prime numbers. So this is pretty much easy. So we consider this as induction hypothesis. And one more theorem that I want to add over here is that there are infinitely many primes. There are infinitely many primes. Alright, so for example, if possible, there are only finite number of primes. There are only finite primes. Now, if there are only finite primes, I'm just assuming a number that is n that is equal to the product of these finite primes. Let these primes are p1, p2, p3, so on up to some pn. This is finite number n, which is stopping at some n. Now I'm just using those all finite primes, and I'm just using I'm multiplying all these finite primes, p1 into p2 into p3 into so on into pn plus 1, just adding this plus 1 at the end. Alright, now from this we can say that n does not belong to this finite number of primes. Alright, and now n does not belong to this, or maybe n belongs to this, and for example, if n belongs to prime numbers, n belong to prime, so that means there is a prime number in the above series that we have included here, does not contain n, because because we are using all these primes, and this n is greater than all these primes. So n belongs to prime does not suits well, because we have taken n equal to finite. We assume that there are finite number of primes, so we are getting some number which is not there in this number list that we have listed over here. So that means n is if n belongs to prime, then there is nothing to prove that from that we can get there are infinite many primes by repeating the process for n plus 1, n plus 2, n plus so on. Alright, so n belongs to prime is trivial case. Alright, from this we can write trivial. Now if n does not belong to prime, alright, if n does not belong to prime, there is some prime among these primes divides this n. I'm considering this pi divides n. Right, if pi divides n, and also pi divides this pn, this p1 series, p1, p2, p3, so on, pn, because we have selected this pi from the infinite series, and that pi, because this n equal to some this number, so that means one of the prime must divide this n by the previous theorem, so by the previous theorem that we have seen. So from that that implies pi divides the linear combination of these two. That is what we have seen. Pi divides this part right over here and this part right over here. Pi divides a linear combination of these two, or you can write pi divides n minus p1, p2, so on, pn. You can. There is also one proof. Actually, I missed it to explain. That is. The GCD of two numbers can be represented as linear combination of two numbers, right? That is, we have already seen. So from that we can say that it divides both addition of these two number that we got and also the subtraction of these two numbers. So this is pretty much same. If the addition of two numbers, linear combination is addition, so if we want to add subtraction over there, that also implies that D divides, because D is a GCD and it does not matter if the values are in plus or minus, so I can use plus and minus both as well here. Because why I'm not using it here is because I want to cut this out, this prime list. Now we know that the value for n equal to p1 multiply p2 multiply p3 so on pn, right, plus 1 minus this p1 p2 so on pn. From this we get this and this get cancel out, so that's why I've used minus. That's it. Pi, that implies pi divides 1. Now do you know that is there any prime that divides 1? No, only one. There is only one possibility, that's 1 should divides 1, and we know that 1 divides every number. Alright, and if pi is not equal to 1, then the theorem is okay. So from this it says that pi divides 1, that implies pi should be equal to 1, or if pi is not equal to 1, then that does not satisfy that n is a number which does not belong to these finite numbers, and from that we can conclude that there are infinitely many primes if we go on repeat this process. For proper steps you can follow your book or from wherever you are trying to learn from. Alright. Okay, next theorem that we have here is, okay, so actually I'm stopping the video right over here. In the next video I'm going to cover the fundamental theorem of arithmetics, which is we have already familiar with, but just it's a proof for that. So best of luck for your preparation of your examinations, or thank you very much for watching the video.